Okay, that I will start my presentation. Hello everyone. Today I will introduce the paper Macrostratigraphy, Insights into Cyclic and Secular Evolution of the Earth's Life System. And the first author is Sean E. Peters. He graduated he got the PhD degree in the University of Chicago and got the Bachelor of Science in Denison University. And his research emphasis is quantifying the rock record at continental and global scales in order to better understand Earth's history and the role that the formation and destruction of rocks plays in governing the evolution of the Earth's life system. And also, he built a lot of database to solve the problems during his research, like the paleobiology database, microstratigraphy database named Macrostat, and the geological map database, and the geo deep dive database that we Ce Zhang gave us the presentation before. And he also built a rock mobile app.
Could you turn to the next page, or could you unshare and share again? I'm afraid that we cannot. And I think when you share your screen, you don't have to show full screen. So just keep where it is. Probably we can see you move to the next slide because we just saw your cover slide. Yeah. It looks good. Yeah. So if it freeze again, you don't have to use a full screen. Just use the previous.
Okay.
Yeah, I think it should be okay. Now it looks okay. Yeah, I think this is okay. I will add a few points to that because we invite the speaker, let's say David Quinn, and I think this next slide that he's going to talk on Wednesday. And for Peter Shan, of course, he's the PI that initiated this. So they began to do this a little more than a decade ago. And that's the first example, so far as I know, in geology. They try to invest the problems through this artificial intelligence, a database-driven process. So at the beginning, what they did was that, okay, they could have the right to download about 5,000 papers a day from Elsevier. So so each year they could download a little bit, like 1 million to 2 million publications. So they stayed there for a couple of years. And so they grew to several millions. And then they try to do the natural language processing and trying to train the languages, train the algorithms to identify which fossil is in which stratigraphy, and which stratigraphy has a certain amount of fossil. So it's pretty simple sentences, by human logic, but you still have to train them to make it work. So they download the millions of publications, and then they use these algorithms to search for the frequency of the different fossils occur in different stratigraphy. So this is a pretty simple idea. And then they counted for how many times certain fossils occur in a certain stratigraphy. And that, of course, goes to some very big questions that for paleontologists, that's people who study fossils, are interested in. And so that people study for different stratigraphy, and as well as in structural geology, for example. So then later on, they expanding that in different other research directions. Actually, they went a little far, as far as I know that they even going to investigate the different writing scale, different writing style of different novels that are written throughout human history. So that's a little bit interesting, since they do have a database, so then they're trying to make the best use of that. So we read it. I do think that they are doing something that's really interesting because they began to propose another perspective into investigating the same question. So after that, then current different other fields, I think mineralogy, geochemistry too, including us, that we are basically doing some more similar thing, but in different subdivision. Okay, so Liang, please go ahead.
Okay, so later I will introduce the logical of the paper. So the left side is about the paleobiology. And first, they find a phenomenon that is famous in the paleobiology. That is, the more number of the rocks, then the more number of the fossil, then the biology diversity will increase following the number of rock fossil. And after that, they formulated hypothesis named the common cause hypothesis. And when the repeaters know the common cause hypothesis, he wanna verify the hypothesis through the microstratigraphy methods. So he built a big database called microstates. And the database contains many rock samples and fossil samples from all over the world. And he analyzes the data in the database and got results to verify the hypothesis. And the other results can reveal the continental evolution. And the common cause hypothesis can reveal the biological evolution. So after they got the two results of the biological evolution and the continental evolution, it can reflect the macroevolutionary is about the life Earth systems. And first, this slide is about the background. They find a phenomenon among the three things: rock, fossil, and biology diversity. The first one that find the phenomenon is the rock. He found it in 1976, and he know that all such estimates of the fossil diversity were subject to a well-known sampling effect. That means the larger the sample of the specimens, the larger the number of taxa. And after that, another paper that he published is also not this same phenomenon, and he's the one who built the common cause hypothesis the first. And before that, the Newell, who recommended this phenomenon in this theory in 1959, that he noted there was a common driver that affected major changes in both the sedimentary rock record and the biosphere. And the geologists covers and the other scientists also recommend this hypothesis, and they do many researches to verify it. And many people want to know the real things about the hypothesis, so they want to analyze the phenomenon from the big data. And there are some challenges to compiling so many data. And there are first main reasons. The first is about reaccessibility the data required to measure the spatial and temporal properties of all rocks, because it's very difficult, and many scientists compile their own data in their own papers, and it's in the different formats, and they and it's in different key points. So if you want to compile this kind of data, you need to compile all kinds of formats of the data. And the second one is about managing and using any such compilations. It needs strong informatics solutions to encompass so many kinds of data, and it needs a strong data structure to contain them. And the third one is it will be the most important. The reason is about there is a tendency among the scientists to view results from large compilations with some skepticism. They will doubt about the result from the big data because it's not the truth in their eyes or in their calculations. And the author built a big database named Macrostratigraphy, and they contained 949 region columns that comprising the North American datasets, and also contains 132 continuously cord basement datasets. Is penetrating from the offshore drilling sites. And this is the website page of their database. And this is the mapping about their data. Their data contains all over the world samples, and the black point is the marine samples, and the blue and green and purple is about the continental sample. And their samples contain a large scope around the layer. And they analyze their data and find the left side is about the marine samples, and the right side is about the terrestrial samples. And they find among the three pictures of the marine samples, the sediment areas and the number of the general and the number of the first. So they have some certain similar tendency. Like they will up in the left and down in the middle and up again later. So there are the same phenomenon about the terrestrial pictures. They also have the same tendency. They will increase following the increasing of the age. And after they know the relationship between the rock and the fossil and the diversity, they want to know if there is some theory or some tendency about the rock cycle, and they could know it and to reveal the tendency of the fossil or the diversity. So they make the huge time and the volume plots about the sedimental rocks. And we could see they have evolution about the plots. And the left one is plot by the Gregor in 1970. He thought the tendency is increased, and they will have some down tendency in the middle. And after that, he insists that they may have some certain increasing tendency. But after that, the Gabriel in 1971, using the same data to plot another peak feed line, and he used the plot to compare with the plot of the Gregor. He finds there are a certain down tendency in the middle of the plot. So it mustn't be a certain increasing tendency. So after 10 years, Renover use more data to fit a detailed like the right picture. There must have some cyclic wave tendency about the rock value number, and there will have some discontinuities in the plots, and they want to know what is the discontinuity, and they also plot another picture, and they combine the the bottom one is about the ocean crust, and the top one and two is about the continental crust. And we could find there are certain relationship between the continental crust and the continental igneous rock, and they have the tendency like the episodic fluctuations, and is with little long-term trend. And about the ocean crust, the tendency is about a decline tendency, and is almost approximately exponential. And this kind of differences means there are some complex relationship between the oceanic crust and the continental rock, and it may reveal the rock cycle. And just now I mentioned the discontinuity, and they want to know what is the exact things that cause this kind of peak or down tendency. So they find a nature phenomenon. It called the gray unconformity. And they have two main formation mechanisms. The first one is about the cryogenian glaciation. It means the glacier will erode the rock layer, and it will make the rock lake some certain layers. And the second mechanism is about the composite surface amalgamation. It means is like the phenomenon that's one of the composite surface that form from many smaller surface, which is caused by multiple independent technical events. And they made another plot about the gray unconformity. And the top one is about the igneous rock in the gray unconformity. And the bottom one is about the sedimentary rock in the great unconformity. And there are some parts have the same tendency, but in earlier parts, they are very different. And they didn't explain so many about the plot, so I can't explain more about the differences. And that's all. Thank you.
Okay, question from our participants today?
Hi, Liang. Thanks for the summary. It just looked like a very a long and difficult paper to go through, so did a good job summarizing it. Did they use their software to compile the data that you presented here, like the Macrostrat? Is that what was used to show the surface area and of the oceanic and continental crust, or how did they get those plots?
This kind of plot.
Towards the end, you showed the exponential function for the oceanic crust and the cyclical for the continental crust. I think slide 11 or later. 13, slide 13. Did they discuss how they computed the area?
The main area is about North America, and they also have some other data about Asian or Australia or other and other place.
And how did they compute area?
They didn't mention it detailed. They just plot the picture, and maybe I will read more about the paper.
Okay, I'm just curious if it was something that comes out from their software, or if it is something that required extra work for them to do. And I'm not sure, maybe Zhangzhou, you can speak to this. Is Macrostrat related to the that paper mining work that Davin was doing?
Yes, like I say, this is all from Peter Shan's lab. So my guess for that, probably we'll get asked them on Wednesday, but my guess for that is that they just use the natural language processing. So they're trying to identify the different names, the different locations. And then for those locations in the papers, of course, they train the languages to identify what types of rocks they are in each location. And then once now they have, let's say, 10 million publications. So among those, I don't know how many of them describe the different types of rocks, because those 10 million publications comes from all categories published in elsewhere, from material science to so far as what we collect, I think is should be in order of 1 billion or less. So for those, they could look for different locations and what types of rocks are. And then I think that then they just plot that to summarize. I think another important crucial thing is that how do they really get age right? I could tell that they could get it from stratigraphy. I don't know how high the time resolutions they could provide to. So that I'm not sure. And my intuition when they make the plot is basically through the natural language processing, rather than from the image identification. Although I think they're also trying to do that, but I'm not sure. Does this really comes out? I would guess the former in terms of natural language processing, rather than the latter, that is the image processing.
Right. Yeah, it'd be interesting to see how they do validation and calibration of things like age and what their general accuracy is. It's very interesting. I think that also that one point is in an earlier slide that said the geological community has some skepticism on these types of databases. And that's a good point of discussion, and probably something you've thought about when compiling your database as well, or compiling these types of databases, is that people will always, people that have done the collection will feel kind of defensive about their data, and they'll say, they'll believe their data, but they might not believe other people's data, and they probably won't believe a big collection of data. And I think that's a human nature thing. So I think in terms of like communicating uncertainties in your database is essential to get these people to kind of use these types of techniques more commonly. Otherwise, people will just want to stick to their own data. So I don't know if that's something that you've come across when you talk to people about this kind of work, big data type of work?
Okay. We'll probably could ask more about that. Okay, so when you think that in Cenozoic we don't have much fossils? I think that makes sense. Probably in Cenozoic, especially more recent, then there's not enough time to form fossils. You need to have sedimentary rocks, let them deposit and then make them into sedimentary rocks. I think that also takes time, millions of years time scales at least. So that probably is a little difficult. Okay. I don't know. I'm another paleontologist. I'm also curious about that. So number. Okay. Do they only incorporate in fossils, not any? Yeah, I don't think they include any modern botany or trees into that. Okay. Yeah, okay. Now I have another question for you. That when you evaluate their age here, so what's the resolution, or how high resolution could they really push to that? Because if they only depend on stratigraphy, then each stratigraphy will have a range of ages. So some common practice that people do is that people look for those volcanic ash deposited in different stratigraphy, because okay, so once at a certain time in geological history, a large volcanoes erupt, then a volcanic rash are going to distribute around the globe in all places, in all stratigraphy. So they deposit together. Then among stratigraphy around the world, people at that age, people are going to recover some of those volcanic ash, and then people do all kinds of radioactive dating for those volcanic ash, and therefore the certain age of this stratigraphy. But I think there's still, I'm not an expert on this, but my curiosity on that is so how high the time resolution could it go to? Because you could have analytic uncertainty for different volcanic ash, that's okay, but one stratigraphy doesn't will accumulate for much longer time scale, because a volcanic eruption just one glimpse throughout the time period of this stratigraphy. So I don't know how high time resolution could this really go to. I think that also means that how do they get the beans from this work? Because they have to assume certain beans here, and normally it's okay. Everyone could, let's say, push beans extremely small, but sometimes if the beans too small, it's just not reasonable, because the resolution is not.
The resolution of the sample is not so high. It is just about a certain error. They only can make sure the sample in the certain certain layer. It means in several hundred more age. in this detailed resolution.
Oh, you mean several millions of years? Is that what you mean?
Yeah.
Okay. Okay, so okay, then that basically still about the analytic era for radioactive dating.
Okay.
Yeah, because for example, in Trentau's case, then at this age, for example, 1%, 5%, analytic era, that's about it. So you have a 300 million year old rock, then you would expect that its analytic uncertainty will be 3 or 15 million years. So that's pretty much about. Okay, yeah. You find a sentimentologist, then I have just 1%. That depends on what people use. Like 5% probably are old, really old data. And 1% is pretty good, and go to 0.1%. That's extremely good. You find a sentimentologist that I would ask about how long does the stratigraphy really take, because it still takes some time, millions of years scale. Maybe that time is shorter than the analytic era. Uncertainty we have to date the radiatic system. If that is the case, then it does matter. If it does matter, then I bet there are. I think. Well, zircon dating is isotopic dating because it still use. Well, for zircons, you also use isotopes because it's isotope is a radioactive decay. That's how people calculate ages. So it just depends on what you're looking for. You can use a boggle rock for whatever, or say argon. There are many radioactive system that people have been using to take samples. It's a whole disciplinary called geochronology. Okay. Luyan, we are expecting you to talk more about the data sets, the database.
I didn't read more about the paper they published in 2018 about their database. So maybe I will introduce later the next presentation.
You mean like next reading? I thought later means, let's say, 5 minutes from now. Okay. Any more questions from our participants today? Okay, I think that's about it. Then Wednesday, we're going to hear the speaker to introduce their work, and I think that probably should have some more update from this side. My knowledge about what they do was about 4 or 5 years ago. So I think a lot of new things have happened. Also, I think they are the first, let's say, large, let's say, NSF funded geology data related large project, I think. I mean, and not in those, like say, seismology. I mean, that's a real geology. I think probably that's the first one funded by NSF for doing for this. So they have a lot of clusters at the University of Wisconsin, and the core part that developed that at the very beginning, in days when Peter Shannon was doing that, was that he was working with Stanford University. So another back then he was a PhD candidate, Ce Zhang. Now he's an assistant professor at the ETH in computer sciences. So they developed the dive So they call the geo deep dive. So he gave a talk here, and we have those talk links on YouTube as well as Bilibili about Johnson's talk, how the dive works, and of course Johnson himself, he's very interested in using the different tools he has help with different natural scientists. So later on he also worked into those astronomy, has the astral dive, and also went into the plantology. So for people who study plants, as far as I could remember, so he went really diverse, using the similar structure, and of course, later on, other people that are trying to use the tools that has developed and then trying to improve that. For example, Shanghai Jiao Tong University, they improved the geodive into a deep shovel, which is currently used at the DDE at our School of Earth Sciences here at the Zhejiang University. So it's interesting, and I do think that Peter Shan made a very important contribution to the community. Not exactly what they directly find, like the way they summarize in this paper, but it's more like the way that doing science that is innovative, and finally read a person and then made it work, and they can make some discoveries. I think that's pretty interesting, and that's also important contributions to our community. Okay, but that, I think that's end of it. Let's see the speaker on Wednesday, and but that, I think that's about it. Have a good day, everyone. Bye-bye. Thanks, Luyan, for leading the paper, and we're looking forward to talk more about that in the future. I bet we will have future speakers continue talking about similar topics.